Well, thank you very much. This workshop has been a lot of fun, so I'm going to give a talk. So I was sort of asked to give a talk at the last minute, and so therefore I apologize. The southeast here refers, of course, to the southeast of France, right? So I'm going to give a talk on the Steinberg representation. And so this is an important representation of certain groups that appears throughout mathematics, in geometry and in topology and in number theory and so on. So I'm going to give a basic introduction to it and discuss some new results. And so what's the main player here is what's called the spherical Tietz building GLN, which is a gigantic bundle of words, but it's really a basic object. What it does is it encodes the sort of combinatorics of elementary linear algebra. And what do I mean by that? So let K be any field. I don't mean a fancy field. Think Q or maybe a finite field. And here's what the Tietz building is. It's a simplicial complex. We call it Tietz sub n of K. And what is it? So I have to tell you what the vertices are, what the edges are, what the triangles are, and so on. So the vertices are non-zero proper subspaces of KDN. And then the simplices are flags of subspaces. And so you have, the vertices are just single subspaces. The edges are two subspaces, one contained in the other, and so on. So this is a sort of, as I said, it's a combinatorialization of linear algebra, right? So if you think about, what do you learn when you're learning linear algebra? You have matrices, they act on K to the n, and you sort of see how they move subspaces around. This is somehow taking that and extracting the sort of combinatorial geometry of it. So here are some basic remarks. So the maximal flags, they have n-1 terms, and the reason is we do not allow 0. We don't allow the 0 subspace, and we don't allow the total subspace K to the n. So everything has dimension 1 less than the like dimension between 1 and n-1. So therefore they have n-1 terms. But remember, because we're doing topology, a single thing is a 0 simplex. There's a sort of shift by 1. So what this really is n-2 dimensional. It's an n-2 dimensional simplicial complex. Let's think about some very special cases just to think about it, what kind of space this is. So the easiest case, well, for n is equal to 1, this is just the empty set. There's no non-zero proper subspaces of K to the 1. So the first interesting case is n equals 2. And so Tietz sub 2 of K, well, all we have are lines inside K squared. There's no containment relations. We don't have any planes in K squared, right? And so all this is a discrete set of lines in K squared. And we have a name for that. That's just the discrete set projective space P1 of K. Okay, so it's just a discrete set. But actually, as you'll see, you think this is the dumbest possible thing. Actually, I'm going to spend most of the talk talking about this example right here. And you'll see that there are non-trivial things to say even here. Okay, so that's the first example. The next example is Tietz sub 3 of K. That would be what do we have in K3? We have lines and we have planes, right? And so therefore, this is a bipartite graph. The vertices are lines and planes in K3. Right? We have lines, we have planes, and the edges are containment. Okay, so this is all this is. This is like a bipartite graph. You have lines, you have planes. You can go from a line to a plane that's bigger than it, and then a plane back to the line. So I want to convince you, it's really a concrete object. It's a graph. It's not that hard to think about. Okay, that is the Tietz building. Oh, by the way, this is a connected. I forgot to say this is the Tietz building is always connected. Starting for n equals 3, and well, let's think about why it's connected for Tietz 3. Well, if we have two distinct planes, P1 and P2, we want to find a path between them, right? So that's enough to prove it's connected. Now, of course, if you have a line is always contained in some plane. So we want to find a path between two distinct planes, P1 and P2. And how do we do that? Well, we have the following path. Wait a minute. What happened? So there's supposed to be a line at the bottom. I'll tell you what that line was supposed to say. I don't know what's going on here. There it is. Yeah. Okay. Okay. Yeah. Anyway, here it is for just. I remembered what the last line was. I could have written on the board, but I bet you I later got myself in trouble if I tried to keep doing that. So for distinct planes P1 and P2, here's the path. You start from P1. Well, because these are distinct planes, they intersect in a line, right? So we go from the plane P1 to the line P1 intersect P2, and then back up to the plane P2, right? So it's a connected graph for teats 3, and you can, the same argument works in general. I mean, you can, if you want to get between, if you're in like teats sub n, you need to be able to connect two n-1 dimensional subspaces, right? And if they're different, their intersection is something that's, it's some non-trivial subspace, right? And so therefore you just go from one to the intersection back up. So this is always some connected simplicial complex. Okay, so that's that. And now what is the topology of this? Well, there's a famous theorem of Solomon and teats that says that teats sub n of k is actually homotopy equivalent to a wedge of spheres of dimension n-2. Remember, the dimension of the space is n-2. So let's think about some special cases of that to see that that fits in with the examples that we talked about. So well, remember, teats sub 2 of k, that's just literally the discrete lines inside k squared, right? A discrete set is also called a wedge of S zeros, right? So that is consistent with this statement. Not a problem. And by the way, like a wedge of S zeros, this is a non-empty, it's there's many, for any field, there's, anyway. So I don't want to. I have this like bad tendency. I'm not very disciplined, so I could actually spend like 5 minutes talking about the empty set to make sure that I was getting my conventions to work out. So I'm not going to do that. So teats sub 3 of k. Well, that's a connected graph. A connected graph is also called a wedge of circles. This is a familiar argument, right? So to topologists, if you have a connected graph, I'll do it right here. If you have a connected graph, there's a vertex, there's a vertex, there's a vertex, there's a vertex, and let's just put some edges between them, What do you do? Well, all you do is you choose a maximal tree, right? There's a part of a maximal tree, and then there's another one right there. There's another one right there. And then you collapse it. So there's 3 different edges you see, A, B, and C, that are not inside the maximal tree, and you collapse. And we get a single x right there, and then we get 3, in this case 3, we get A, we get B, and we get C. And we get a wedge of 3 circles, right? And that works for any connected graph. For any connected graph, you choose a maximal tree, and you collapse it, and you get a wedge of circles. And so therefore, connected graphs are the same thing as wedges of circles, up to homotopy equivalence. OK, and so that's what this theorem says there. 3 minus 2 is 1. OK, and so this is the sort of generalization of this fact right there. And in fact, the proof is sort of similar to this. Instead of what the real theorem says is, so this is an n-2 dimensional simplicial complex, and you prove that it's n-3 connected by doing a sort of combinatorial argument. I mean, there's many proofs of this now, but they're sort of they all come to sort of intersecting lines and planes, finding subspaces that are highly connected you can collapse to a single vertex and so on. Okay, so now we have this beautiful space encoding linear algebra, and the point of linear algebra is not to look at vector spaces, but to look at matrices, right? That matrices actually come first, and then vector spaces come second, right? And so this was born so that gln of k can act on it simplically, right? So the linear action of gln k on k to the n permutes lines and planes and 3 spaces and so on. And so it acts continuously on this simplicial complex, and therefore it acts on the homology of this simplicial complex, right? And well, there's only one interesting homology, namely the homology in degree n-2, right? Because these are wedges of n-2 spheres. Therefore, that has a name. That's called the Steinberg representation. So the Steinberg representation of gln k with coefficients in the complex numbers is, we write it Stn of k, and it's homology in degree n-2 of this teats building with complex coefficients, just because I want this to be a complex vector space. And I take reduced homology just to make sure this reduced homology is what you should do in the degenerate case n=2 to make this work out to be the thing you want. Okay. So this is a complex vector space. It's some complex vector space defined, in a fairly concrete way, but it's got a complicated action. And the general linear group acts linearly on it. In other words, it's that's that right there. So this is another name. This is a representation of the general linear group. So remember, if you have a group, a representation of that group is just a vector space upon which that group acts linearly. So this is a special distinguished representation of gln k. I moved the definition up because I don't expect you to remember every slide, to the next one. So then move the definition at the top. Let me make some observations about it. So the first thing is this is finite dimensional exactly when K is a finite field. Okay, if K is a finite field, then of course there's finitely many lines, planes, and so on inside K to the n because K to the n is literally a finite set, right? And so, and it's not easy to, the converse is also fairly easy to see. So this is a finite dimensional representation exactly when K is a finite field. And in that case, it was introduced by Steinberg, as you might expect from the name. And in 1951, he proved this fundamental theorem that says that for a finite field, STFQ, the STn of FQ is an irreducible representation of the GLN of FQ. Okay, so what does that mean? Just to remind you, this is topology talk, not a representation theory talk. Well, it is a representation theory talk to an audience of topologists. So an irreducible representation of a group, what that means is that it's a vector space upon which the group acts, and the only subrepresentations are 0 and v, the two sort of obvious subrepresentations. And so there's no like parts, like this thing is there's just one piece of this representation. Okay. And so let me make some remarks about this. So first, when you look at GLN-FQ, that's like to my mind, so this is maybe like a little piece of philosophy, right? When I teach abstract algebra, when I teach group theory, it's easy to think that the most important groups, like the basic ones, are like dihedral groups and symmetric groups and stuff. But really, what I think of groups like GLN-FQ as the sort of typical finite group. These are the finite groups that sort of show up in mathematics all over the place. And it really has a lot of internal structure. But one thing about it, well, GLN-FQ, like you think, oh, this acts on FQ to the n. That's an easy representation. That was the thing it's born to act on. But it's a finite group. It should have lots of interesting representations over the complex numbers, but it's not so easy to find any of them, right? GLN-FQ does not act on C to the n, right? There's just no way to make it act like that. So non-trivial, well, there's one-dimensional representations because GLN-FQ you can take the determinant that maps to FQ cross, and so you can act by rotations. But in dimension, if you have a representation that's more than one dimensional, it's actually usually quite high dimensional. So these are not so easy to write down. Okay, but they do show up in nature, and this is the most fundamental of them. It plays a basic role in the representation theory of GLN-FQ. When you develop the representation theory of finite Chevalley groups, the Steinberg representation sort of shows up throughout the representation theory in various ways. And so this is in some ways the basic representation. But of course, this is not an audience of representation theorists. Why should someone that cares about geometry care about this? And so, well, this was given at groups in geometry in the southeast of England before. So I said, why should geometric group theorists care about the Steinberg representation? So let's pretend some of us are actual geometric group theorists, some of us can pretend, right? So why should you, as someone that cares maybe about things that are more geometric, why should you care about the Steinberg representation if you're not care about finite groups? Well, the place this shows up in geometry is due to a basic theorem of Borel and Serre. What does it say? So I'm going to state it right here. There's some undefined words in this. So the symmetric space Xn for SL and Z. So SL and Z is the basic example of an arithmetic group. These are lattices inside semi-simple D groups, in this case SL and R, and they have a natural space they're act on called a symmetric space. I'll give you an example in a second. And so the symmetric space, remember I've talked about the moduli space of curves, and I said it's not compact. And you sort of want to compactify it. That was a thing we did yesterday, right? And Borel and Serre compactified these symmetric spaces. Well, so the symmetric space Xn for SL and Z has a bordification. You can add a boundary at infinity, and the boundary turns out to be homotopy equivalent to this Tietz building. Okay? And I want to explain that. This is a mysterious statement because it's hard to think about these symmetric spaces. They're sort of high-dimensional, complicated spaces. Maybe they're not part of everyone's education, but there is one that is part of everyone's. Oh, in other words, this is just a sort of slogan. The Steinberg representation is the homology at infinity of SL and Z. But let me give you an example. So there is one example of a symmetric space that I think should be part of everyone's education, and that is the symmetric space for SL2R or SL2Z, and that is the upper half plane. Okay? So that's a space, so SL2R acts in the upper half plane by linear fractional transformations. That's one that we talked about last time. So that matrix, in that case, a matrix ABCD takes Z inside the upper half plane to AZ plus B over CZ plus D. And I even drew a picture, like there's, This picture I found easier to hand draw, but you can see my handwriting. As you've already experienced, my handwriting is not that good, so I apologize for the quality of my pictures. So here's a basic picture that I think many of you have seen before of how SL2Z acts on the upper half plane. Well, here are some basic elements. The matrix 1, 1, 0, 1 that acts by z goes to z plus 1, and so that's sort of horizontal translation. And that takes, this line right there to that line right there. The other basic matrix right here would be 1, 0, 1, 1. And that takes z to -1 over z, right? And so that right there has, well, it has a fixed point at I, right? I goes to I, and it's sort of like a rotation around that. Maybe that wasn't, okay, anyway, so those are, that wasn't 1, 0, 1, 1. Okay, sorry about that. So this is the last minute talk, and now my mind is blanking on exactly what matrix that is. But you all, I guarantee you there are people in the audience that know, and you can figure out what matrix takes z to -1 over z. I guess that would be 1, 0, 0, negative, or maybe, which one? Oh yeah, 0, -1, 1, 0. That's right. I wanted to have determinant 1. I apologize, yes. So that's a fine order matrix, yeah. And you can see what that's sort of doing is it's sort of taking this point I and it's rotating around that point I right there. And these two matrices generate SL2Z, and you can sort of see that what they're doing is they're sort of inducing this, this is a fundamental domain for the action. this side of that is being identified with that side of that. This edge right there is being identified with that edge. It sort of gets flipped around like that. And so if you quotient out of the upper half plane by SL2Z, you get the famous modular curve. It's it's a sphere minus a point topologically. It has two special points. It has the image of this purple point. That's right there. And it has this image of this red point. That's because those are the sort of two orbifold points, the two cone points. And then it also has one cusp at infinity. The cusp is when you go up right like this. Okay, so this is a classical picture. I think many of us have seen it. And so what Borel-Serre's theorem is saying is that we can add a boundary at infinity to this upper half plane where the boundary is homotopy equivalent to the Tietz building, Tietz 2 of Q. And let's see why that is. So how do we boardify the upper half plane? We want to attach a boundary, but it's sort of hard to do that because you have to take points and add them to it, and then you have to somehow define a topology, and that's not so easy to do. But Grace had a beautiful idea. This works for all SLNs. If you have a manifold and you think that there should be the interior of a manifold with boundary, the way to find that boundary is you chop off a neighborhood of infinity, right? There should be a Collar neighborhood at infinity of the boundary. And if you chop that off, you can find the boundary inside your manifold. Okay, and so Grayson said, let's do that. And in this case, it's much easier to do that. So we're going to chop off the neighborhood at infinity. And so here's a picture. So infinity, remember, there's one cusp. Remember, we saw the picture of the modular curve, one cusp going up. And so that right there is the region above that horizontal line right there. That's called a horoball. You take the SL2Z orbit, and it's going to be this packing of balls on here. So each of these, is an orbit of the region. This is z greater than or equal to, the imaginary part of z is greater than or equal to 2. That's the region above that line right there. And then the orbit under that, under SL2Z, are all these disjoint balls, and you see they get packed really tightly along the boundary right there. Okay, these are what are called horoballs. They're tangent to the line at infinity. Okay, and I said that's what our neighborhood at infinity is. So that's an SL2Z invariant neighborhood, and let's just chop them off. Okay, remove those, and that's going to be what our boardification is. And so, if we remove those neighborhoods at infinity, well, in the modular curve, we're chopping off the cusp, right? And so the quotient's compact. So we've removed part of H2 such that the SL2Z is now acting co-compactly. What does the boundary look like? Well, you might think the boundary is a bunch of circles, right? It looks like a bunch of circles, but that's not right because they're tangent to this boundary at infinity, and that point is not actually there. And you can see that also because here's one of those circles right here, which is tangent to the point at infinity. And so what these really are is they're copies of the real line that look like they're closing up at infinity, but they don't actually close up anywhere in the world that exists. They close up sort of only after they pass to the edge of the universe. So really the boundary of this is a disjoint union of copies of the real line. Okay, you have a copy of the real line for each of these balls. Like here is like you take a circle and remove the bottom point, and it's just like there's a real line. Remove the bottom point, that's a real line, and so on and so forth. Okay? So the boundary of this chopped off, this sort of bordified space is a bunch of copies of the real line. There's one tangent to every rational point plus the point at infinity, right? So you have one, this is tangent to 0, this is tangent to 1, this is tangent to -1. Those differ by translation, and then this is tangent, I think, to 1, I think that's, well, if that's 0, that's 1, that'll be tangent to 1/2, and so on. So you have all those things right there, but now what is Q union of point at infinity? That's another name for projective space, P1 of Q, because every lines inside Q squared are determined by their slopes, right? And the slope can be any rational number plus or infinity if the slope is, it's 1/0. And so therefore we see that the boundary of this sort of bordified space is homotopy equivalent to the discrete set of lines inside P1 of Q, because each of these real lines right there is really a point to the viewpoint of topology, right? They're contractible. And this is another reason why this is sort of a subtle result, because it's not going to be the case that the boundary at infinity is going to be literally a copy of the Tietz building. It's going to be something that's homotopy equivalent to it. It's got some kind of thickened Tietz building like this. Okay? Here we've taken each point in this discrete space and sort of thicken it up to a copy of the real line. Something happened in the higher dimensional case. It's harder to visualize, but that same sort of thing is happening. But that's why people that are interested in geometry should care about the Tietz building, because it really plays the fundamental role in understanding the topology of arithmetic groups like SLNZ. Okay, are there any questions about this? Yes. Right. Yeah, the problem is that won't be like for one, the bound the action of SL2Z on R is very chaotic, right? Like you're going to get something where the quotient is not even Hausdorff, I think, right? Because it sort of mixes up R like too much. Yeah. Right, exactly. Yeah, you take the rational points, but then you blow each of them up to a real line. Which is, if you wanted to find this by attaching a boundary at infinity, what you do is for each horoball here, you want to attach this point, and you sort of make it so as you travel into this horoball, you're approaching that boundary right there, that boundary line at the infinity. Yes? Yeah, but not off the top of my head. So, yeah. I think the Ford circles are the maximal one, where you choose it so they're all tangent to each other. And I want to take something where they're not tangent, like I just make them just a little bit smaller so they're all actually disjoint. Any other questions? So this is why I care about these. So now, of course, that last thing, the sort of arithmetically or topologically interesting Tietz building is the Tietz building over an infinite field. So what's known about that case? So if the field is infinite, like if the field's Q, then STN of K is an infinite dimensional representation of an infinite group GLNK. But when you learn about representations of infinite groups that are infinite dimensional, you think, oh, they're probably maybe they have a Banach space structure or a Hilbert space structure or something. But this is literally a naked vector space with a group action. There has no structure whatsoever. It's not algebraic. It's not continuous. You are confronted with an abstract naked group and an abstract naked vector space on which the group's acting. And therefore, there are no tools for studying it. Like that's somehow representation theory of infinite groups is usually very hard, and it's especially hard if you're not if you don't have usually the ones that we have tools to study are things like unitary representations or things. But this is sort of outside the bounds of what representation theorists know how to work with. But there are some previous results about these Steinberg representations. So there's a theorem of Zhai. So remember I told you that Steinberg proved that the Steinberg representation over a finite field is irreducible. So the algebraic closure of a finite field is like a union of finite fields, right? And so in 2014, Zhai was able to use that sort of, it's just like a limit of the finite dimensional ones to show that Stn of fq bar is an irreducible representation of GL and fq bar. And then there's another theorem. So I should say, like, I asked on Math Overflow many years ago whether the Steinberg representation was irreducible for infinite fields. And so this was, you know, a question. I assumed it was known, and it turned out it wasn't known. But in response to that, you know, Galatius, Coopers, and Randall-Williams in 2020 managed to prove that, in fact, well, they couldn't prove it's irreducible. They proved it's an indecomposable representation. What that means is that you can't write it as a direct sum of two subrepresentations in a non-trivial way. So it's weaker than irreducible. I mean, pardon me, because an irreducible says you have no subrepresentations. This says you can't break it up into the sum of two subrepresentations. Okay? They did many other things in that paper too, but I was very excited. Like, you know, I was at a conference, and I think Soren Galatius was giving the talk, and he announced it as a solution to my Math Overflow question in one of the slides. It's kind of, you know, exciting. Anyway, so I should say that, like, if you learned about representation theory for finite groups, then indecomposability and irreducibility are the same thing, because if you're looking at representations of finite groups or algebraic groups, everything decomposes as direct sums of irreducibles. They're semi-simple. But that's just not true in this setting. There's no such thing. There's nothing like that can possibly hold. So, well, there's my main theorem. I guess that's from that setup, there's only one theorem I could tell you, right? And so this is it. This is a theorem myself with Andrew Snowden, which says that for infinite fields K, the Steinberg representation Stn of K is an irreducible representation of GL in K. So this works for any infinite field. And so we now have a complete theorem. But in fact, it's more general than that. So the Steinberg representation, as I've been describing it, is something about GL and K. So GL and K is a basic example of what's called a reductive group. And there are many other reductive groups in the world. Things like the symplectic group is a reductive group. Various kinds of things preserving different kinds of forms and stuff like that. So these are, you know, and for every reductive group, there is a Steinberg representation. So our theorem has no hypothesis. It works for any reductive group. And I had to learn, you know, I didn't know, you know, the ones that you and I know, maybe I don't want to say, the ones that I knew before I started thinking about this stuff were the split examples. Things like GLN's a split group, the symplectic group's a split group. But there's a vast world, if K is not algebraically closed, there's a vast world of reductive groups that are not split and have an extraordinarily complicated structure. So this works with there's no hypotheses. The other thing is that I defined the Steinberg module to be a homology with complex coefficients. So these were complex vector spaces. But in fact, our theorem has no hypotheses there either. You can replace the complex numbers with any other field at all, whatsoever. And that tells you that our theorem really has something to do with infinite fields, because it turns out that for finite fields K, there exists other fields F, so that the sort of Steinberg representation over capital F is reducible. So our theorem is really a theorem about infinite fields. Like there's like the general theorem we prove has no hypotheses about the coefficients, and so therefore it can't possibly work over arbitrary fields. We have to use the infiniteness somewhere. So what I want to do in the rest of this talk, so I don't usually prove theorems in talks. I think of that as too much. But it turns out that in this case, if you strip away and do the easiest non-trivial special case, it becomes completely elementary. And like but elementary not like in like a boring way, but it uses, I think all the ideas appear, but in such a simple way that I can explain them to a general audience. Okay? And so what I'm going to do is, for the rest of the talk, is I'm going to prove this theorem for GL2K, the simplest special case, where there's the structure of the building is just a discrete set, right? So you don't have to worry about the topology of the building anyway. And I'm also going to assume that K is characteristic 0. It's harder if K is finite characteristic. But for K is equal to Q, which is the case that sort of, you know, that like, or other algebra, or other algebraic number fields, you know, this is the case that's irrelevant anyway. So I'm going to prove that completely. So for instance, for K is equal to Q. So, and you're going to see the reason it simplifies is because in this case, the proof, what it's going to do is I'm going to reduce it to a statement about ideals and group rings. But those group rings, the groups in this case turn out to be abelians. These are ideals in abelian group rings of abelian groups, and so therefore that's commutative algebra. So it's, in general, you have to do non-commutative algebra. And so what I'm going to do is I'm going to very carefully reduce it to something about ideals in group rings and sort of commutative ideals in certain commutative rings, and then I'm going to reduce it to finite characteristics. So it's going to be a reduction to finite characteristic argument. So this is a theorem about fields of characteristic 0. So there's somehow it's elementary, but somehow uses like neat techniques that are useful in other contexts. Anyway, so now I'm going to do this, but like I said, don't worry. Like I'm going to remind you the definitions of the objects as they come up at us. Okay. So first, I have to remind you of the structure of the Steinberg representation. So this is we're just doing n equals 2, and so here's a definition: let U2 be the 2 by 2 strictly upper triangular matrices over our field. Okay. That's matrices that look like this: 1 lambda 0 1 with lambda an element of k. This is an abelian subgroup of a group, right? Easiest group of matrices imaginable. It's the unipotent radical of the parabolic subgroup, of the Borel subgroup, pardon me. So the maximal parabolic. So anyway, minimal parabolic. My brain is, I'm very tired since this is the second hour I'm lecturing. So what I want to do, and this is something like this is true for any Steinberg representation, is I claim that there's a vector space isomorphism between the Steinberg representation and the group ring of U2. Okay, and let me explain what that isomorphism is, because this is something very elementary. Remember, what is the Steinberg representation? When you take Tietz 2, that's just the discrete set of lines in k squared, right? So lines in k squared, and the Steinberg representation is just, well, it's h0 of that, but reduced h0, right? That's where that I was careful to work in reduced homology for the degenerate case, because the degenerate case is the one I'll be caring about. So what does it mean? What is the reduced h0 of a discrete set? Well, these are just literally formal sums, Ci, Li, where Ci is a complex number and Li is some line, right? And the sum of the coefficients is 0, because we're in reduced homology, not unreduced homology. Okay, that's all this is. And so that's what the Steinberg representation is in this very degenerate case. Is this just formal sums of lines where the total sum is 0? Okay, that's all it is. And I claim that that we can come up with a vector space isomorphism between that and this group ring of U2. And well, how do you do that? Well, here's a basis for the Steinberg module. Well, I told you the total sum has to be 0. So one possible basis is you choose some line. Here's a line. I'm using projective coordinates, right? Homogeneous coordinates for projective space. This is the line of slope 1 over 0, the line of slope infinity. And so that's just that line minus some other line. Any other line will be of the form lambda comma 1. Okay, so this is a basis for the Steinberg module. And look, 1, 0, lambda 1, 1, 0, lambda 1, right? This has, U2 has that. The basis is in bijection with U2. And that's what the isomorphism is. Oops. The isomorphism iota just takes this basis element 1, 0, lambda 1 to the matrix 1, lambda 0, 1. This is a basis element for the Steinberg representation. This is a basis element for the group ring, right? So I've just put the bases in bijection with each other in the most naive possible way. So it's a vector space isomorphism. But you should say, what the hell, Andy? That's not... Like, I care about representations. Like, these are just vector spaces. I put them in some funny bijection with each other. What is that good for? Well, I moved that definition up because I don't expect you to remember it. So the Steinberg representation is an action of GLNK. The group ring of U2 does not, right? Well, it does. So iota induces a really weird, we have this vector space isomorphism. We get a really weird GL2K action on this group ring, right? I don't know, like, if someone asks me how does GL2K act on this, I have no idea, right? There's not an obvious action. Well, there is for some part. So U2 is a subgroup of GL2K, and there it's the usual one, right? So U2 itself acts on C of U2 by left multiplication. So on part of GL2K, this is sort of matching up the actions of the two. But on the rest of it, all bets are off. It's sort of, the left-hand side is a very natural action. The right-hand side is a sort of unnatural action. That's right, yeah, just literally as a vector space, yeah. This is not I'm not thinking of it as a group ring. I'm thinking of it literally as just a vector space. I have a weird action on a vector space. So what this tells me, though, this tells me something. So this says if I have a subrepresentation of the Steinberg representation, I want to show there aren't any, right? That tells me that if I hit it with iota, I get an ideal in this group ring, right? because so at least now I've matched up on the left-hand side subrepresentations, on the right-hand side ideals. But of course, there's more group acting on the left-hand side, so these aren't any ideals. These are special ideals. Because U2, so U2 acts on ST2 of K, and it also acts on the group ring on the left in the sort of usual way, the left regular representation, right? And so this map is equivariant with respect to that. And so if you have a subrepresentation, it's preserved by the action of U2. That maps to something over here, which is also preserved by the action of U2, and that's what an ideal is, right? An ideal will be a sub-vector space that's preserved by the left action of U2. Right? That's literally the definition of an ideal. Right? It's closed under addition, and it's also closed under a left multiplication by your ring, right? It's a submodule of your ring. Make sense? Well, so I'm using much less than that. All I'm using, so because it's a GL2 subrepresentation, it is in particular a U2 subrepresentation, right? It's preserved by U2. And so therefore, its image is also preserved by U2, because that's the only, on that subgroup, this actually matches up the actions. Yeah, U2 is in fact a subgroup of GL2. That's right. That's very important. And that's the only piece here where it's easy to see what the action is. Well, except there's one other bit of the action that's not so hard to see. And that's how do diagonal matrices act. Diagonal matrices act very nicely. I claim they act by conjugation. So how do diagonal matrices act on this basis? Well, a diagonal matrix is the form D001, right? And so this acts, well, it takes 1, 0 minus lambda 1 to, well, D comma 0 minus d lambda comma 1, right? But of course, these are homogeneous coordinates, so we can rescale, and this becomes, this just becomes 1, 0, and this one we can't rescale. It just becomes, it's still d lambda comma 1. So diagonal matrices act in that way on this basis. They permute the basis, right? Because they preserve 1, 0. They preserve the line of slope infinity. But if you think about how they act on U2 by conjugation, it does exactly the same thing. If you conjugate this matrix, you get 1 d lambda 0, 1. And so therefore, these aren't just any ideals. These are ideals that are also preserved by the conjugation action of diagonal matrices, which has a certain expansivity property, which we'll see. OK? Any questions about that? I'm going to move that to the top. You don't have to remember much else after this. Okay, but well, I'm not going to move this to the top. I will remind you of this. We have ideals preserved by the diagonal matrices. But now there's one other thing. So what I'm going to basically prove is that if you have an ideal in this group ring that's preserved by the diagonal matrices, then it's got to be the whole thing. That's sort of what the main theorem is going to say. If you have an ideal here that's preserved by the conjugation action of diagonal matrices, it's the whole thing. But that's not actually true. That can't possibly be true. And the reason that can't possibly be true is because there is one obvious subrepresentation. There's one obvious ideal. There's the augmentation ideal. So remember, let epsilon from the group ring to C be the augmentation. It just adds up the coefficients. And so therefore, I have to fight against the kernel of this augmentation. That's the sort of battle I have to win. And so here's a claim. For all non-zero x in the Steinberg representation, I can hit it with an appropriate element of GL2K such that its image in the group ring has non-trivial augmentation. And let's see. This is just linear algebra. So here's an element in the Steinberg representation is a linear combination of lines, right? C0, L0 to C and Ln, where the Ci's are non-zero, the Li's are distinct lines, and the sum of the coefficients is 0. But now the sum of the coefficients of the Steinberg module is not the same as the augmentation on the right-hand side. There's sort of two different augmentations here, and don't confuse them. So how does this work? Well, what I'm going to do is I'm going to pick G inside GL2K to move this L0, that first line in this list, to the line with slope infinity, line 1, 0. That's my distinguished line. And then GLI is equal to lambda I1 for some lambda I, doesn't matter what. And so what does GX equal? GX is equal to something like this. It just takes the first thing to 1, 0. Then we have lambda 1, 1 up to lambda n1. And if I rewrite this in terms of my basis, what is this thing? Well, it's going to be, remember the sum of these coefficients is 0, the CIs, and so therefore this is the same thing as, well, C1, this minus that. That's, well, there's a minus sign there, up through minus Cn times that. So if you expand this thing out, you're going to get the right coefficients in front of each of these things. You might worry you're going to get the wrong coefficient in front of 1, 0, but you don't, because the sum C0 is equal to the sum of the coefficient, like is equal to negative the sum of the coefficients. So you do get C0 in front of 1, 0. Okay? That's great. That means the augmentation, what does the augmentation do? If you hit this with iota and get the augmentation, you're adding up these coefficients, that coefficient up to that coefficient, and that's negative C1 minus up to minus Cn. But that's the same thing as C0, right? And that's not 0. That's all it is right there. So it really is playing the two, we have two augmentations. We're sort of playing them off each other when we do that. OK, that's that. Let me summarize what we've done. We've made two different arguments, and I want to put them together. So remember, our goal is to prove that ST2 of K. So remember, the sum starting at C0 is equal to 0, right? But the sum starting at C1 is not 0 because it's, yeah, that's what's going on there. Any questions? I'm going to summarize everything that I've done, so you don't have to remember the individual arguments, just sort of with the pieces. So our goal is to prove this is an irreducible representation, right? Well, what do? So we take a subrepresentation, which is not 0. We want to show it's the whole thing, right? We map it over to the group ring, and we get and we call that I. And what is I? It's an ideal. We argued it was an ideal before, right? It's also closed under conjugation by diagonal matrices, because diagonal matrices act in this nice way, right? And it's also not in the kernel of the augmentation map. This is all you have to remember. We don't need to remember anything about Steinberg, so our goal theorem should say that this means it's the whole thing. So our goal theorem is equivalent to an ideal in the group ring that's closed under conjugation by diagonal matrices and not in the kernel of the augmentation has to be the whole thing. This is like an elementary commutative algebra statement, right? Because this is this right here is it's a commutative ring. So this is like a pretty nice commutative ring, really. So that's the kind of thing that we have to prove. And I should say, like, the general case is actually sort of like this, except now you have to deal with non-commutative rings and ideals and non-commutative rings. And you need all this work. There's deep work of Philip Hall on the ideal structure of these things. And it's the sorts of things that go into Hall's theorem saying that polycyclic groups are residually finite. The same sorts of techniques that go into that are used for this. So at least in characteristic 0. In characteristic P, you have to do some number theory. In any case, that's what we're going to prove. OK. So that's our goal theorem. You can now forget about the Steinberg representation. We just want to prove this statement of commutative algebra, this commutative algebra statement. And the way to prove it is to generalize it to a theorem that has no hypotheses and prove that. Like, we're going to keep saying something that seems more and more general until there's nothing to do. So, OK, use the torus. The diagonal matrices are also called an algebraic torus. That's if you're in, if you work in the world of algebraic groups, for some reason a torus to you is the same thing as a group of diagonal matrices, which definitely don't form a torus to a topologist, but it is what it is. So yeah, it's a maximal torus. Yeah. So an ideal closed under conjugation. That's the theorem we want to prove. OK. So now what do I know? So since I'm kernel of the augmentation map, I can find some element x inside it such that the augmentation of it's not 0, and I just scale it to make the sum of the coefficients equal to 1. Okay, so I can find some element of that form in there. And now, since it's closed under diagonal matrices, and a diagonal matrix D1 takes this, it just multiplies that by D, I get that this element XD, Ci of 1 D lambda I 0, 1, is inside I, right? So I start off with this one sort of element inside my ideal. And I generate a whole list of other things inside my ideal. I have x1, x2, x3, x4, and so on. And formally, what I want to show is my goal is to show that x0 is in my ideal, because what is x0? Well, x0 is, well, you multiply the upper right, upper right-hand corner by 0. It's ci times the identity for each I. The sum of the ci's is 1, so that is literally saying that the identity matrix is inside my ideal, and therefore everything is. It's the whole thing. It contains the unit, right? You know, to show that an ideal is the entire ring, you have to show the identity is contained inside it. That's all you have to show. And so I have these elements, x1, x2, x3, x4. If I can formally show that those are all in the ideal, if I can formally show that x0 is in the ideal, then I'm done. OK. You can forget most about this. OK, so I want to prove that x0 is inside I. How do I do that? Well, I'm scared. Like I told you that this group ring is a pretty nice commutative ring, but there's problems with it. It's not Noetherian. And that's not allowed. Diagonal matrix 0. You know, if that were in there, we'd be good. But that's unfortunate. Yeah, it's not. The diagonal matrix 0, 1, 0, 0, 0, 1 is not invertible. So, if only we were allowed to use the 0. If you're allowed to use non-invertible matrices, most of our lives would be a lot easier, right? So, in any case, though, the one bad thing about this is that it's not a Noetherian ring. It's not like a polynomial ring or something. And I am scared of commutative algebra over non-Noetherian rings. So we're going to reduce to the Noetherian case now in a formal way. I'm going to define a ring homomorphism from the ring of integer Laurent polynomials to this by just taking zi to 1 lambda I 0, 1. And so thus, zi to the d goes to 1 d lambda I 0, 1, right? So I have a ring homomorphism like this. I've got my ideal. So, well, I've got my ideal I inside C lambda U0. Well, because I have a ring homomorphism, that becomes, in particular, that ring homomorphism makes the group ring into a module over this ring of Laurent polynomials, which is a much nicer ring. Like, this is the sort of ring you study in commutative algebra, right? And it has a submodule I. So as I said, I'm going to reduce the hypotheses more and more each time. And so I have this special element, xd is equal to, you know, zi, you know, this thing right here lies inside I for all d. And I want to show that that also holds for d is equal to 0. That's my goal, right? And the way I'm going to do that is I'm going to prove that something like this basically holds with no hypotheses for anything. I will prove something that works for arbitrary modules over a ring of Laurent polynomials. Here it is. Here's the lemma. If you have a module over the ring of integer Laurent polynomials and invariables, and you have a submodule, and you have elements m1 through mn, which are inside m, such that the sum of zi of the d, mi is in n for all d at least 1, then, in fact, the sum of the mi is inside n. This is like, this is all you need to prove, right? And in fact, you can prove this directly by just using like identities between power sums and stuff like that. But I'm not good with sort of classical commutative algebra. So I'm going to do somehow non-classical commutative algebra. OK, well, the first thing is you might as well assume that n is 0, because you just replace the module by m mod n, right? Why not? I can also assume that m is finitely generated, because I just replace it by the submodule generated by the little m sub i's, right? So I have a finitely generated module. And so now, let alpha be any maximal ideal in my ring. And what's it enough to show? So I want to show, my goal is to show that the sum of the m sub i's is equal to 0, because n is now 0. And it's enough to show that an element of a module over a finitely generated module over a nice ring like this is 0. It's enough to show it becomes 0 when you localize at any maximal ideal. Okay, if you're 0, and if you learn a little algebraic geometry, like, you know, localizing at a maximal ideal, it's sort of like looking at a point, right? You have a module, it's like a vector bundle over some variety. And this says that if you have a section of that vector bundle and it's 0 at every point, then it's actually the zero section. So this is the kind of thing that if you study commutative algebra is like an automatic like Pavlovian response on how you prove a theorem, right? If you think of modules as like sections of vector bundles and you have some section you want to show as 0, well, it's enough to show it's 0 at every point, right? That's how you do it. And that's what this is literally what that means in algebraic geometry world. I promise, okay? So the Kroll intersection theorem says that that's equivalent to showing. This is a basic theorem. It's in Eisenbud, you know, or I think it might be in Atiyah McDonald too. It's a theorem. I was only allowed to teach commutative algebra one time in my life, and I did teach this theorem before I wrote this paper. And the Kroll intersection theorem says that to show that you're 0 in the localization, it's enough to show that you're inside the intersection of alpha to the r of m for, you know, as r goes from 1 to infinity. Okay, that's how we do it. So fix some r. Then if we mod out, so alpha is a maximal ideal in this ring, right? And if we mod out by alpha to the r, well, that's a finite ring. I've now reduced it, you know, so I'm studying a finite ring. The z1 through zn are all units in this finite ring because these are Laurent polynomials, right? So I have z1, but I also have z1 inverse. And so I have units in my ring. It's like a subgroup of the group of units. And so therefore, what that means is because it's a finite ring, each of these things is a unit. So therefore, there's some common power of them all, which is 1, right? If you have a unit in a finite ring, some power of it's got to be 1, right? And so then you can choose a common power that works for all of them, a GCD of whatever, right? So we can find some d at least 1 such that zi of the d is 1 mod alpha to the r for all I. And that means that 0 is equal to, well, I know that that's, you know, d is at least 1, so I know that zi of the d mi, that sum is equal to 0 because it lies inside n. So I know that that's 0, but that's also the same, that's as 1. And so that's what I prove. That's why I need to prove. There's nothing to show. That's it. So this is a very strange argument to me. Like in some sense, this is as I said, somehow like I'm trying to prove something and I'm reducing it to characteristic P. That's what this somehow going to this finite ring is sort of doing. And so it's a, you know, it's a curious argument, but it really is elementary. And so this was, you know, and the general case is actually fairly similar. The general case, though, as I said, it uses all this work of Philip Hall on the sort of intermediate results. He proves a bunch of intermediate ring theory results on the way to proving that polycyclic groups are residually finite. So it uses that at least in characteristic 0, and then it uses some more number theory and characteristic P. But anyway, that's the proof. That's what I wanted to say. Thank you.